In 1964, a physicist named John Stewart Bell published a paper containing a single inequality. It relied on nothing more than basic logic and arithmetic. Yet these few lines of math created a direct, testable challenge to Albert Einstein's lifelong conviction about how the physical world must function. Einstein spent his career arguing for a universe that was predictable and orderly. He believed that the apparent randomness found in quantum mechanics wasn't a feature of nature, but a failure of our own measurement tools. To him, the universe was a clockwork machine. We just didn't have the full blueprint yet. This belief was built on a concept called local realism. Local meant that objects are only influenced by their immediate surroundings, and realism meant that those objects possess definite properties whether someone is looking at them or not. This wasn't just a preference for Einstein. It was the logical foundation upon which he built his entire scientific worldview. Einstein illustrated his logic using a simple analogy. Imagine we take a pair of gloves and place each one in a separate box. I send one box to Tokyo and the other to New York. When the box in Tokyo is opened and reveals a left glove, the recipient immediately knows the glove in New York is the right one. This isn't magic or faster-than-light communication. The gloves had those specific left and right identities from the moment they were packed. Einstein argued that quantum particles work the same way. He suggested they carry hidden variables, internal instructions that determine their behavior before we ever conduct an experiment. We see randomness only because those instructions remain hidden from us. It's an incredibly persuasive argument because it matches how we experience the world every day. It feels safe, logical, and, most importantly, obvious. However, when we actually test the behavior of entangled particles, the glove analogy begins to fail. When we measure these particles at different angles, we see correlations that are mathematically stronger than anything the glove analogy allows. The particles appear to coordinate their states with a precision that simple pre-hidden instructions cannot explain. John Bell's genius was in finding a way to test this limit. He proposed an experiment where entangled particles are sent to two detectors, each randomly switching between three settings, A, B, and C. Bell used pure logic to calculate a correlation ceiling. He asked, if these particles truly have fixed hidden properties, as Einstein believed, what is the absolute maximum frequency at which their measurements would match up? He successfully moved the debate out of the realm of philosophy and into a space where it could be settled with a calculator and a laboratory. Bell's math produced a hard limit, the number 2. This is the mathematical boundary for any universe governed by local realism. In Einstein's world, the correlation value can never go higher than this. Quantum mechanics, however, predicts a value of 2.828. If the quantum prediction is correct, it would mean the very foundation of Einstein's local realism is mathematically impossible. In 1982, physicist Alain Aspect put this to the test. He recorded the results of thousands of particle interactions and found a correlation value that climbed well beyond Bell's limit of 2, landing exactly where quantum mechanics predicted. In the decades since, increasingly sophisticated experiments, including the 2015 loophole-free tests at TU Delft, have consistently confirmed these results. The consistency of these results across thousands of trials means that any theory relying on local hidden variables contradicts our physical observations. The math suggests we live in a universe that must be either non-local, non-realist, or both. We're left with a choice. To align theories with data, we must let go of Einstein's assumptions. Path A suggests realism is false. Particles have no definite state until measured. Path B suggests locality is false. Events influence each other instantaneously across any distance. Most modern physicists now operate under the assumption that both are partially true. The universe lacks definite states before measurement and maintains these strange non-local connections. Despite settling one of the most significant debates in the history of science, Bell's theorem is often absent from the standard physics curriculum. It remains a subject that many students only encounter in advanced graduate-level seminars. It took nearly 60 long years for Bell's proof to be fully recognized with the 2022 Nobel Prize in Physics, a testament to how long it took for the scientific world to internalize these results. Bell's math directly targeted the core assumptions of the classical world, the concept of naive realism, the rule of local causality, and Einstein's deterministic model. John Bell started this work as a side hobby while working as an accelerator engineer. He provided the definitive proof that the universe is far stranger than our intuition allows. As we look back, we are left with a universe where properties appear to manifest through the act of measurement itself. If the interaction is what defines the state of a particle, we have to ask what is physically occurring during that transition. We'll explore that collapse in Episode 4, Quantum Decoherence. See you there.